Hi, my talk today focuses on observing hail and the newer approaches we're exploring for measuring hail shape, structure, trajectories and distribution. So this work was completed by myself and Alan Pratat at the Australian Bureau of Meteorology and also supported by Matthew Kumjan at Penn State University. So to kick things off, I'm going to talk about what I call the hailstone problem. So we know that hailstone trajectories and growth are mutually dependent on each other, which makes it quite a complex problem. You can see, for those who aren't familiar with these concepts, I have a diagram on the right showing an idealized convective storm with the feeder clouds, updrafts showing red arrows and downdrafts with the blue arrows. We have our hailstone embryos being ejected from the feeder cloud across the updraft region above the freezing level, well above the freezing level, which is our hail growth region. These trajectories then descend down to the surface, well at least some of them. So we can see that small changes to the environment or parent storm can lead to large changes in these trajectories and the properties of the hail growth zone, which presents a challenge when we're trying to predict these properties. Furthermore, hailstones move through these regions at sometimes high velocities, and thus conditions for them change rapidly. Altogether, this makes in situ or remote sampling of natural hailstones very difficult to unfeasible. Conventionally, hail is sized from reflectivity alone and transposed directly on the ground. An example here demonstrates mesh, where we've integrated reflectivity in a column. Above the freezing level, it is weighted appropriately, depending on the temperature, and transposed onto the ground with X millimeters. This is a fairly simplistic approach because it does not consider both trajectories or growth. Modern radar retrievals using polarimetric information and 3D wind retrievals are able to better overcome these limitations. An example here from Brook et al. Shows us that once we initialize our hail size within our radar samples, we're able to run 4 trajectories, providing a more realistic estimation of the hail swath at the ground. However, validation for these new retrievals is still most often inferred from ground observations, which is not ideal when you have trajectories aloft. Simulations for growth has also been demonstrated over the past few decades, most recently by Kumjan and Lombardo 2020, and work is planned to extend this to nowcasting in the future. However, validation of growth as well is also absent. We have some requirements moving forward beyond these problems to get better measurements of our hailstone swaths and our hailstone shapes. So some requirements we have from our modelling dependencies are drag coefficient, force, speed, advection, and size distribution. When we're considering growth, we need a bit more information, and this includes collection shedding rates, thermal exchange rates, and internal processes such as soaking and freezing. So this is quite a complex arrangement of properties we need to effectively model hailstone trajectories and growth. Observing these properties and processes is very challenging, of course, due to the hostile nature of hailstorms, and conventional measurements are traditionally ground-based, such as disdrometers and reporting, and have changed little in recent decades. So the following slides presents new and adapted techniques that increase the sampling, accuracy and insight we can gain from hailstorms and hailstones. So starting off with shape, and the most important attribute about shape is that irregularities increase surface area. You can see on the right here we have a 5.2 centimeter hailstone, and it's showing some irregularities, but overall it's approximately a spherical hailstone. So this is important because the surface area affects thermal exchange rate, changes the aerodynamic drag, and impacts the electromagnetic scattering. When we have increasingly large hail, such as this example here, we have a 13.3 centimeter hailstone collected in Brisbane. We see that increasingly large hailstone becomes increasingly irregular, and this increases the surface area, which leads to greater cooling rates, increased collection rates, reduced drag in some cases. Despite all this, the spherical representation is still widely used for both retrievals and simulations. Just to highlight the importance of getting better estimates for the shape properties of larger hailstones, I've shown here a plot from Shed et al. 2021, where we can see the equivalent diameter on the x-axis plotted against the measured diameter from 3D scanned hailstones on the y-axis. And you can see for larger hailstones, they're becoming less and less spherical. To measure shape, the most accurate way is to use a digital 3D model. This is first demonstrated in 2017 by Ian using an infrared 3D scanner. So in Australia we've developed a low-cost approach where we've used a DSLR and photogrammetry software, and this has been applied to recent hail collections, including the second largest measured hailstone in Australia. On the right you can see an example on the top of the 3D scanning technique using a handheld scanner, and on the bottom the setup required for photogrammetry, which involves a DSLR camera on it and a turntable. We hope that by developing this new technique and lowering the requirements for 3D scanner, we can see a larger collection of community hail models available for analysis. Moving on to growth regime now. And we know that remote sensing growth is very difficult. However, if you consider hailstones like paleoclimate archives, the layers can actually be used to understand their formation. So some examples of this are that clear ice indicates a hailstone surface temperature of approximately 0 degrees Celsius. And increasingly opaque ice reflects the fact that the freezing was faster for collected water, and in this process it has trapped air bubbles. So the volume, the ratio and the layering of different growth regimes provides an indication of the growth conditions throughout the hailstone's growth trajectory. So this can actually provide important validation for both simulations and also reconstructing thermodynamic trajectories. Hailstone cross-sections were widely used in the 1960s to 1980s for reconstructing hailstone trajectories. It is time-consuming though to prepare samples and analyze samples. So more recently we've been exploring the application of computer vision, and this is designed to automate the detection and measurement of layers within hailstone cross-sections. And you can see an example on the right, a composite panel of 40 hailstones collected in Melbourne, which we are about to apply this technique to. This technique is designed to provide an objective measurement that runs instantaneously. So one of the outputs from this technique is an equivalent circular representation, which can be directly used for validating growth simulations. Moving on now to trajectories. And we know that hailstone trajectories are a result of complex interactions from the larger scales down to the microphysics. And conditions in hailstorms are complex, with strong turbulence on fine scales, and this is in part why we have such diverse trajectories. An example of this on the right is a figure from Brook et al. 2021, where we've got a 3D wind retrieval from a hailstorm in Brisbane in 2014, and Jordan has inserted 3 17mm hailstones into this retrieval and run 4 trajectory simulations. You can see these three hailstones inserted at different heights take remarkably different trajectories. So it's very important to map these trajectories correctly if we want to understand both growth and predicting the area of impact. So in terms of their application, trajectories can be used to correct for hail advection, as Jordan demonstrated on the right, and also for simulations to more accurately predict hail growth, such as the work by Kumjin and Navarro 2020. However, there is some question about the representativeness of these approaches when we are considering sub-grid scale turbulence. A novel approach which we're exploring to improve the direct measurement of trajectories is adapting serial microsonde technology, which includes an embedded tether released attachment into hailstone-shaped probes, and these probes are released into updraft regions via a balloon. So primarily these probes measure GPS and also measure pressure and skin temperature of the probe. One of the biggest challenges in developing this new technology is limiting ice accretion, because we do not want the aerodynamic properties and the mass of the probe to change during its measurements. So we're carefully designing active heating and icing coatings to help combat this. And also the design has to be resistant to collisions and landing. So we're currently preparing for field testing, which is planned later this month and into April. Last but not least, size and concentration. So we all know that hail should be represented by a distribution, and small samples of population such as what we can get from ground-based sensors, can sometimes limit our capacity to reconstruct the true size distribution. Reports are even more challenging, because from a single report, it's impossible to know whether a hailstone represents the 75th or 50th percentile. Radar retrievals and microphysical schemes treat hail as an idealized distribution. However, we're not really sure in some cases how representative this is of reality. The first approach for tackling this problem is to use aerial measurements, and this is a technique which we demonstrated in Relapco in 2018. So using a drone with a 20 megapixel camera flown from 10 millimeters, we're able to capture very high resolution imagery, approximately a 2.7 millimeter pixel resolution, over several hundreds of square kilometers. And this enables us to sample, in some cases, tens of thousands of hailstones. So from this imagery, we use a combination of computer vision and machine learning to detect and measure individual hailstones. And you can see an example of this imagery on the top right. From this dataset, we're able to reconstruct very robust distributions of the maximum and intermediate diameter and their axis ratio. An example on the bottom right is from a more recent Melbourne hailstorm event where this technique was applied. And finally, it's not possible sometimes to have hail pads across a city or even fly a drone in several locations. So one unique approach which we're looking at is using hail-damaged car bonnets. And recent advances in scanning technology allow for rapid assessment of vehicles at a high precision. And we're talking about approximately a 1 millimeter measurement of dints on these vehicles. So using this technology in collaboration with an Australian insurer, we collected 100 hail-damaged bonnets following a major hailstorm in Melbourne in early 2020 to explore the mapping between dint size distribution and hail size distribution. So for this event, we also had an aerial survey very close to several of the bonnets, which allows us to explore the robustness of this relationship. And once we're happy with this, we'll start exploring the spatial variability of this relationship as well. So we hope in the future that for significant hailstorm events, we can extract potentially hundreds of hail pads in a very quick manner using this new technology to look at the spatial distribution of the hail size. And finally, in summary, so we've gone through a lot today, but a couple takeaway messages. So hailstone trajectories and growth have significant potential for improving current nowcasting services. However, observations are needed for their development. So one approach that I've demonstrated is adapting modern technology that allows for increased sampling, greater insight into hailstone properties and evolution. I also want to highlight that individual hailstones are an underutilized dataset we should be looking into more. Application of these measurement techniques I've identified today is ideally suited to large intensive field projects such as the proposed ice chip experiment. And thank you. If you have any questions, please get in contact with me. My email address is on this slide. Thanks very much.